So first of all, thank you very much for joining us today. This is our first event of the newly launched Early Career Network lecture series, the slightly delayed August version titled Building Materials and Environments. The lecture series is planned to run until Christmas, so every month we're going to have an event with a different topic, a different theme in geoscience, and different guest speakers. So today we've got two fantastic speakers who have come to join us. First up is Sara Hoffritz. So Sara is a highly passionate geologist with interests covering a broad spectrum of fields, and she's a former board member of the Geological Society of Denmark. After completing her degrees in Denmark and Canada, her early career took her around the world, from conducting mineral exploration in Greenland, volcano monitoring in Mexico, and she even starred on TV as a scientific expert studying volcanoes in Vanuatu. Over the past few years, she's been based in Copenhagen, working in building materials, and she's kindly speaking to us today about the work she's been undertaking. She's also currently the geology lecturer with an expedition company in Antarctica and the Arctic. So without further ado, I'm pleased to invite Sara to introduce her talk for us today.
Hi, thanks for having me, and thanks for using your first day evening hearing about building materials. I don't know how it is in England, but here it's very nice weather, so it's a lovely evening in Denmark. Let me just share my screen. Are you done, Matt, with your screen sharing?
Yeah, thank you very much.
Do this, and I'll share, and I will do like this. Cool. So I want to give you a small introduction to historical building materials and how you can work as a geologist within this field. Matt already kind of told you a little bit about my background, so this will be quite short. But I used my bachelor and my master thesis looking much into mineral exploration. I had this luxury problem while studying that I thought every subject within geology was interesting. And so I thought mineral exploration was a good way of kind of collecting the geochemistry, the structural geology, sedimentary, metamorphic, everything under one umbrella. But unfortunately, when I graduated in 2014, there wasn't any mineral exploration happening. So I had to figure out something else to do. And as Matt mentioned, I did a little bit of volcanoes and I did a little bit of environmental geology before I finally found my new umbrella, construction industry that also allows me to work with structural geology and geochemistry and sedimentary and igneous and metamorphic petrology. So a lot of all the fields that I really love to dig into. I started back in 2016 at a small company in Denmark called Pelcon, where I work with petrographic analysis of modern concrete. I'm not going to dig too much deep into that because I think we're going to have a talk that's a little bit more concrete orientated. But since 2018, I changed to an even smaller company, also based in Denmark. We are 3 people working on this, and we work on petrographic analysis of historical building materials. And we do this all over Northern Europe. So we look at mainly buildings of heritage value, so castles and churches and archaeological, I cannot pronounce this word in English, but archaeology sites all over Denmark, Sweden, Norway, and Finland. So usually our customers are heritage boards, or it's architects that are working on renovations, or it's archaeologists that have different projects. So building materials, so mainly we look at mineral-based building materials. We look at mortars, so the glue that you use to glue bricks together with. Mortars you also use as renders or plasters on facades and buildings. We look at the bricks themselves. We look at concrete that's usually a little bit older than this century. And then we look at building or sculpture stone, natural stone. And then we also look at paint layers. So actually quite a lot of different types of materials. And in Denmark, and I also assume quite a lot in England, these are the materials that make up most of our buildings. So you might wonder, why is this geology? Well, I always usually compare mortar or concrete as man-made lava. You have a combination of your phenocrysts, that's your sand in the case of mortars, or aggregates in the case of concrete. You have your matrix that's connecting your phenocrysts, that's your binding material. And in the case of mortars, that can be lots of different types of materials. It can be based on cement, which is a mixture of burnt lime and clay. It can be pure clay, it can be pure lime, it can be gypsum, and all sorts of different combinations. And then you also have your air. So as you would have your air vesicles in your lava, we also have entrained or entrapped air in our building materials. You can also talk about flow structures, both for concrete and mortar. How easy is it to work with? Is it like a Pohoho lava or like an AA lava? Which makes sense for a geologist, that the viscosity is of course different. Then there's also the fact that you have new minerals that precipitate in air voids or in cracks. You can have alteration of your material, like in metamorphic geology, when you have alterations from one mineral to another. We also see that in our building materials. And in general, just basic mineral recognition under the microscope, knowing how to use the microscope, knowing how to recognize a mineral. And then there's the law of superposition. Like, you know that the bottom layer must be the oldest, the top layer must be the youngest. We use this a lot for paint layers, for example. So what you see here on the slide over on the right side here is a baptismal font that is usually located in a church in Sweden, but it illustrates the murder of Thomas Becket. So right now it's actually, I think, in a museum in London somewhere. And I took out a few small samples from this baptismal font. And when I say small samples, I'm talking like 1 × 2 millimeters worth of sample to figure out what paint layers have covered this font throughout time. And that's actually a thin section of the layers that you can see here at the bottom, where one of the samples showed 4 layers of different paint layers that had different colors, and tells a story about what colors has covered this font and how has it changed through time. And with this, we look at, okay, what is the binder material? How did they apply it? What pigments did they use for this? So quite interesting, but also geology. And then we also date our layers, mostly relative, but like how you would use fossils in a stratigraphy dating process, we also do that with some of the minerals that we see, or how the mixture has been of the mortar. So the answers that my customers usually want answered, the questions, sorry, that my customers usually want answered, and the question I always ask myself, depending on whatever the customer wants, is where on the structure does this sample derive from? How old is this material? Is it original, or is it some kind of renovation that they accidentally took out and doesn't have anything to do with the original part of the structure? What is the material composed of? What type of material is it? How was it made? Where does the material originate from? And has the material been altered? And depending on what the customer wants, we usually focus on some of these questions. And the question I want to take you through today is, where does the material originate from? Because all of the questions is used with geological eyes, but where does the material originate from is where you really get to use your geological knowledge. So first of all, this is a picture from under the microscope, and remaining pictures are going to be my small world under the microscope, where I show you what I see every day. This is a mortar, and what is pretty important to mention here is that for concrete and mortar, and we at my company, we use it for all our materials, we impregnate our samples with fluorescent epoxy. That aids us a lot in telling original porosities, original cracks and defects in our material. And it also aids in our thin section production. We make our own thin sections, and sometimes our material is so porous and so weak that we need to have some epoxy to keep it stabilized together. And having it fluorescent means that when we look at it with UV light, it shows the porosity perfectly and cracks and so forth. So everything that's yellow on the picture is epoxy. And the epoxy is pretty much here showing you everywhere where there's air voids. All the white you have here, those are your sand grains. And all that gray mush you have in between, well, that's your binder material. So it's not like porridge, but like your lava, you have your matrix, you have your phenocryst, and you have your vesicles. Then to make a mortar, you have to have your binder material that you, as I mentioned, you can make a very wide different range of materials. And in this binder material, even though it looks very grainy and fine-grained, you can find some elements that indicate what was mixed. For example, if I can get my arrow to show, I don't know if it's showing you guys, but in the middle of the picture, there's a small lime lump. And over to the left of it, there's a small grain of Portland cement. So this is a mortar that has been mixed with lime and cement, so a lime cement mortar. All right, let's see, type of limestone. What do I look for when I try to figure out what the source of the limestone that has been used? So when you want to make a mortar, I don't want to get too technical, but you take some limestone, you burn it, and then you have different ways of mixing it with water and sand to create a mortar. And often when you burn it, you don't get, well, nowadays you do, but if you go back to the past centuries and back to the medieval ages, all the way back to there, you have very uneven burning temperatures. And that means some limestone gets burned at high temperatures, some limestone gets burned at low temperatures. So very, very often we are able under the microscope to find pieces of the limestone that has just been burned just a little bit. And that is quite important because when we look at these limestones, we can recognize where did they get the limestone from? And that's a quite interesting question to answer when it comes to, for example, what has the trading routes been in the 1100, or were there any use of getting Swedish limestone for Denmark in the 18th century, stuff like that, are questions we can answer because we can recognize the limestone. We can differentiate between a Swedish, a Norwegian, a Danish limestone, and within those fields as well. So what type of limestone? First of all, is it sedimentary? If it's sedimentary, what kind of fossils do I have? What kind of grain size is it? What type of limestone is it? If it's marble, I'll look at, is it a pure marble or does it have any other type of minerals? And I always hold this up against where is my sample from? Are there any historical quarries that would make sense? And all these informations, the historical, the archaeologist, and the geologist knowledge kind of mix in together to figure out what type of limestone does it also. Is it reasonable to say that this is a Norwegian limestone in Denmark, for example? So I have a few examples to show you how I differentiate. I don't know if you guys have any sedimentary petrography. I surely did not. I've never looked at a thin section of limestone during any lecture. So this was quite new to me. So it's I'm still learning more and more different limestones under the microscope, but I picked out a few examples for you guys. So the rest is just pictures. This is a quarry from Nob in Jutland. So you have it down here with the map. You have Denmark, and Jutland is the western part of Denmark. And this is a limestone from Denyen that is made up by cocolites. And we recognize that under the microscope because it's very, very fine grained. So this is a picture taken under the microscope at, I think it's 100 magnification. And what you have here in the middle is a grain of underburned limestone. So it's a piece of limestone that has been used for a mortar, and it's been burned just a little bit, but not enough for it to completely dissolve into microcrystalline lime. So what you see here is that this type of limestone is made up of tiny, tiny grains of lime. So we're talking nanofossils, we're talking grains that are less than 5 micromillimeters, so very, very fine grained. This is in plain polarized light, and here you see it in cross polarized light. We also, from the Danyan limestone, have a borozoan part. And we see this more in my area of Denmark, over on the eastern coast. This is a picture from Stevns Klint, which is a UNESCO site, where we have the fish clay that's showing the boundary between the dinosaurs dying out at 65 million years ago. The borozoan limestone of Danyan is also quite recognizable, because there we get our borozoans, of course. So this is again, plain polarized light is 200 times magnification. And the grain you see here has the remnants of the fossil of borozoan fossils. So this is also a way to recognize this type of limestone, because you have this fossil type and it's so dominant in this specific type of limestone. Under cross polarized light, it looks like this. Then we, from Finland, mostly get marble used for making mortars. And this is specifically from very close to Helsinki, where they have the Sipoo marble. And this is from when they were digging out a tunnel throughout the marble. And as you can see, it's not this pure white, clean Carrara marble. It's quite impure, I think it's called, sorry. And this is just to show you an example of the marble. You can recognize it with its lamellas passing through, and very coarse grained. This is at 100 times magnification. It's under polarized light and under cross polarized light. Here we have, this is taking the burning at a higher level. So we took the lump we had before, we took one of these grains, burned it at even higher temperature. And what you see here is I'm trying to outline that the grain is taking up most of the picture. And you see most of the grain has actually turned into microcrystalline lime. But you have all these brown areas, which are the remnants of pyroxene and amphiboles and quartz grains that have not been altered yet. And that's because this is a very impure limestone or marble that we're dealing with. This is under polarized plain polarized light, and this is under cross polarized light. Another example is we often from Norway, not too far away from Oslo, get this dolomitic limestone. And it's quite characteristic that it's very fine grained, but then it has these beautiful rhombohedral dolomitic crystals. So you see, this is at 50 times magnification, but the grain is very big. So if you can see my arrow, I'm just outlining it here. And the grain consists of the macritic part, so it's very fine grained. Then it has these maybe previous cracks with coarse calcite crystals, some sparite crystals. And then you have these gorgeous small rhombohedral dolomitic crystals. This is under polarized light and on a cross polarized light. And then if we take a little step closer, you can really see how nice shapes we're getting here, these diamonds that are scattered through the limestone. And at cross polarized light. One of the rocks we see most used, especially, well, of course, especially in Sweden because it's Swedish, but we also see it in Denmark and in Norway. It occurs in different varieties and it's often used as a facade stone. It's orthosite limestone because it contains the squid of orthoseteras. And you can see it here on the floor from my university, where you can see the squids laying down here. And it has a very specific, unique red color because it's when it was deposited on the sea bottom, it was the same type deposited with some laterite dust that has this yellow oxidized color. Red oxidized color, sorry. And if we look at that under the microscope, these are just the squids. This is a very big grain. Again, you can see, for some reason, I finally remembered to put a scale on. You can see it's quite a big grain we have here. And how we recognize this limestone is we often don't see the squids, but we often have some trilobites or some sea lilies present in the grain as well. And then you can see the dark color. It's more visible on the next picture I have here, where you can see the grain is sort of red in the color. And that's very specific for this Swedish limestone from Öland. This is at plain polarized light, and this is at cross polarized light. Then last but not least, we sometimes come upon oolitic limestone, also from the Oslo area in Norway. And this is from, it's called Brønnøya. It's like a small island. And this is where they used to burn their lime back in the 1400s. And this is an example of the limestone. We always get them as very, very big grains. So this, you don't even get to see the boundary of the grain here. We're just digging deep into it. And what you see here are the oroids that are these spherical shapes in a mass of sparite. And also, again, very recognizable when we get it in the microscope. I'm not sure I have that of cross-polarized. Let's see. Yeah, okay, that's with cross-polars. You can still see you have your oroids, and then you have small grains of quartz scattered through the sparite crystals surrounding the oroids. So those were a few different examples of limestone that I come upon, and this is a big aid when looking at the historical mortars that I look at around Scandinavia. And I look at a lot of other different things, but this was just to give you a little bit of an appetizer of what you can do as a geologist with historical building materials. So questions are welcome, and otherwise, thank you for letting me take your time.
Thank you, Sarah. I'm sure everybody will agree that was a fantastic introduction. I do apologize. I should have said we have a Q&A box at the bottom. So if anybody has any questions, please pop them in there. I'll start us off. So obviously you had quite a diverse start to your career, Sarah, and then you came to this a little bit later. If any of our attendees are thinking they never realized you could use geoscience in this way, how would you recommend they'd go about either as their studies or when they're looking for jobs going into this sort of line of work?
Well, I was kind of surprised because I didn't know prior to getting into the industry that geologists existed in this industry. But in Denmark, and I think also abroad, a lot of geologists are sitting in concrete and in building materials in general. Concrete is a pretty good place to start because it has a lot of more jobs in it. Historical building materials is very research based. So there's not that many facilities that actually look at it. We're the only institution, or we're not an institution, we're the only company that look at it in Northern Europe. I think the UK is very, what would you call it? It's very observant on the field. So I think if there's any place to study it or to get a job within historical building materials, the UK is the place to go. I'm not quite sure. I know there are some different forums, some different societies, some Lime forums where they dig deep into it, and there's a lot of geologists in those. But other than that, I mean, have a general interest for geology. Petrography is a good base to start with. But I mean, I use geochemistry, structural geology, and all sorts of geology in my daily work. So I don't know, being like a not too specified might be the trick.
Thank you. And secondly, you gave a number of questions that a lot of your clients sort of are looking for the answers for. What do they then use those answers for? What's their main driving purpose to undertake this sort of analysis?
Well, it differs on the type of client. Often if it's architects that need to renovate a house or a building, they want to know, okay, what do we have to work with? What kind of material can we use on top of this material? How can we keep the original thought behind it? How do we keep it real to the original material, but still renovate it? It's also, it's not a law, but it's a rule that we have from our heritage sport in Denmark, that before you renovate a house of heritage value, you need to know what it was made of originally. But also we have the archaeologists that just want to know trading routes. They want to know, where did they get the material from? How did they do it? So it's mostly that those questions that the customers have, but it differs.
Great, thanks, Sarah. If we don't have any more questions, should we move on to the next talk? Thank you very much. I thought that was fascinating. It was definitely a great insight to a use of geoscience that I didn't really appreciate, to be honest.
I didn't until I knew it.
So our second talk's by Serdar. Serdar is a fellow of the Geological Society of London, and he's one of our committee members with the Early Career Network. So we're super grateful he's willing to open the lecture series for us. He's a quality management consultant and quality control engineer. He originally comes from Turkey and has 11 years international experience within the construction industry. So if I can pass over to Serdar, invite you to share your screen and introduce your talk, please.
Thank you, Matt, and thank you, Sarah. And also, it seems like we used to work with same company. The construction world is quite small. Pelcon, we used to work with Pelcon in one of my projects. So it seems like construction is like a quite small family. So thank you, Sarah, for the wonderful presentation. And thank you, Matt, for organizing everything and having us as speakers here. So let me just start with my presentation. Okay, let me just share my screen. Okay. So the topic is natural construction materials, the basic concepts, the idea of performance and sustainable design, which will come up in 2022. So a little bit about myself. Like Matt said, I've been in construction industry for 11 years, almost 12 now. And my background is in geological engineering, and I graduated from Ankara University. I also, during my undergraduate, I worked in geochemistry labs and also petrography and microanalysis laboratories, which is kind of my passion. I really enjoy being in laboratories, which kind of helped me to transition to materials testing and research further on. So that's pretty much came naturally to me. But my background is in geological engineering. So like Matt said, I'm also a fellow of Geological Society and in our ECN committee. So before we begin, please follow ECN if you are already not doing it, or please share our events so we will just reach out to more people. And that's out of the way. So first of all, I would like to remind that 2022 is going to be the year of sustainability. Our current year, 2021, is the year of space, and GSL announced sometime in April 2020, 2022 is going to be year of sustainability. So a lot of conversations we are going to have here is going to be relevant in the next year, and I'm sure GSL is going to expand on this subject more. So the focus is going to be sustainable use of materials and also renewable energy sources, and especially focusing on disposal of waste, be it like regular waste or like nuclear byproducts. So, and this is going to require a lot of effort from geoscientists in the UK and all around. So just keep watching that. So okay. Just a short reminder that where we are in materials or construction industry, just a simple figure, it's actually quite has high impact, because as you can see, construction industry accounts for 6% of global share of energy consumption and 11% of carbon emissions worldwide, which is, well, 6 and 11%, you might feel that, oh, it's not that much when compared to transportation or residential, but it's quite high, and the processes involving construction and materials are quite energy intensive, and the technology is not as fast developing as other sectors. So that requires more immediate action than it initially implies. So in 2019 and 2020, due to COVID-19, we had reduction in consumption and emissions naturally, but now that things are getting slightly better and the recovery phase is somewhat up ahead, it's expected that the demand for more construction, more buildings, more transportation structures, more motorways, more railroads is going to be up ahead. So it's supposed to increase in the coming years. Okay, so this presentation is going to focus on two end user products that are concrete and asphalt. For just a small note, whenever I mention pavements, I'm going to be talking about roadway pavements as in American term, so not the sidewalk that we use in the UK. So in case anyone gets confused, so we would like to start with, I would like to start with concrete, which has quite interactions with geology when it comes to materials. So just the basics, concrete is, production of concrete is one of the most energy intensive processes you can think of, especially the production of Portland cement, which uses a lot of resources and really high amount of energy. So, but also it's the cheapest and most adaptable material that you can use. Like I said, it requires quite high energy, but in the recent years, in the recent, let's say 20 to 30 years, there are research about replacing the Portland cement in concrete with industrial byproducts like fly ash, natural pozzolans like volcanic ash, or ground granulated GGBS, what we call. So there's a push towards having reducing the amount of raw material that's used. So that's going to come up a little bit later. So that once we have the Portland cement, we have the second important constituent, the aggregates and fillers, which is quite relevant to us as geoscientists. These can be can be produced as it is from like river beds or just relatively young deposits, or they can be manufactured. And usually this one, water, is it's quite in the background, but it's quite important because the production of concrete requires high quality water that is in many cases that are drinking water. So the specifications require almost drinkable water. So as you can see, this production process requires a lot of materials that is directly needed for human consumption as well. So that's going to be one of the important points. So mixed design of concrete, selection of materials, performance considerations, and sustainability. When it comes to design of a material, especially concrete and asphalt, it is always a balancing act. There is no simple solutions. There are no easy way out. If you increase certain materials, or if you use certain materials, you have to balance out with something else. So it's always a battle between the cost, the environmental impact, the health and safety, the service life. So you are always going to be thinking way into the future, because the effects can be observed way later, which can have really unfortunate results. If anyone following up the building collapse in Florida, which also I'm also following as well. So this is quite important. Mixed design of concrete is quite critical. So as a geologist, as a geoscientist, our battle starts at the very beginning with soils. So basically every soil investigation for any kind of building or any kind of structure requires some kind of chemical testing that's just identifies two critical ions that can be damaging. Also, there are like many other, but the two main criticals are sulfates in the soil and the groundwater, and the chlorides in the soil. So these are going to be really directly affecting the design life and sustainability of the buildings, because the building will deteriorate much faster if they are exposed to these elements. So it also affects the type of cement you are going to choose. If you are in a highly let's say highly sulfate dominant environment, you have to have sulfate resistant cement, which changes almost every parameter in design. So basically what to look out for, what are we looking for? First of all, high concentration of sulfates, especially water soluble. Acid soluble sulfates are not our immediate concern. That's a different type of problem, because if you have an acidic soil, that's going to be a much different problem. But what it can cause is it can cause severe cracking in concrete due to forming a mineral. It's called ettringite mineral, which expands greatly and cracks the concrete. So what's the potential solutions besides identifying the soil structure and the soil chemistry? Is like I said, sulfate resistant cements, or increasing the cement weight and fixed volume, which increases cost and increases the environmental impact, and it makes the concrete too harder to work with. That comes back to, like I said, it's always a balancing act. So what do we have to consider? Like the costs, workability of concrete, setting time, and leaching of colloidal particles. So it's not just always a simple solution by, okay, replace the cement. You have to consider all other factors. And coming to chloride, it's quite simple. You can see in the background, a chloride damages the reinforcement in concrete, which is probably one of the main reasons that service life of building is quite reduced. And I'm sure like it's also quite effective on like the maintenance of, you have to have maintenance if you are exposed concrete like this, or you might have to evacuate building. So this is also a problem in maritime structures, which has higher like splash zones or direct impact with the concrete structure. So again, how can we fix this? You can reduce the permeability of concrete, increasing fine fillers, which is usually derived from, again, quarries with high environmental impacts, or you can increase the concrete cover, which is another subject that increases costs. So we have, like I said, this is just a sample of sample of effects that has on buildings. So what can we do as geoscientists? Where do we stand? Like I said, right the first time, initial geological surveys are the most important factors determining a design of concrete and the selection of materials. So having a good and precise identification of soil chemistry is quite critical. It can prevent much costly mistakes later, and or you can just have much easier time knowing that you don't have any problems like that. And well, the second one is just like Sara mentioned, using what people in the past used, which is natural pozzolans. From since like old Greek times, Egypt, Romans, every civilization use natural pozzolans, which can be volcanic ash or other pozzolans like pumice stone. There's ground up pumice stone. They are quite good binders by their own, but they are quite costly to produce or procure in general, but they can replace Portland cement in great amounts, and they are quite resistant to sulfate and chloride attacks. So that's one that can help us in the future. Also, recycling, another man's treasure. Recycled concrete, sadly, cannot be effectively used in making new concrete due to the chemical reaction ending. So, but the recycled concrete can be used in other items such as fills or landscaping or ground stabilization. So to know what you can do with this material is quite important. And also research, because we still don't know what affects the performance of concrete and what interactions between natural materials and manufactured materials are. So that's also needs to be researched further. And the more research we do, the more sustainable results we will have. So moving on. We are getting into more a little bit specific. So aggregates are the second most important part of concrete. So it's aggregates control the workability, the long-term performance, and the strength of the material, as well as their chemical composition also controls the service life as well. This is where local geology comes into play. Not every country has a good or reliable resources of aggregates. For example, United Kingdom, Southern United Kingdom is more rich in limestone aggregates that are a little bit mixed with chalk in general. Northern, especially Scotland, has more granite or more harder rocks that you get that can be used in aggregates, but they have their issue problem. So and also when I was working in Northern Africa, it was quite inaccessible. Like high quality aggregate was quite inaccessible. When I was working in Turkey, high quality aggregate was quite accessible because Turkey had quite active magnetism, and also it was on the fault line. So you always had large amounts of hard aggregates within reachable distance. So local geology really affects the accessibility and the quality of aggregates. Okay, as a basic property, abrasion resistance and freeze-thaw expansion resistance are what we usually look in aggregates to classify them. So basically, this is it's usually comes up first. And it's probably the most important factor initially. Then you will get into the other qualities. So this is the part that is highly controlled by petrography of the parent rock, weathering, and metamorphism levels. This is quite generalized. There is so many differences and nuances to that, but generally, basaltic rocks or high silica quartzites are quite resistant to abrasion under loads. Limestone is considered like median usually good for structural concrete, but you might need much resistant aggregates for specialized concrete. Marble and gneiss are generally, because of their layered structures, they have quite high abrasion loss, so it's not preferred, but if you have to use it, you have to use it. So that's it. Granite is prone to releasing, especially trapped clays when in the quarry. When crushed, granites tend to release a lot of clay that cannot be used, or that is problematic in concrete. So it needs to be identified, it needs to be studied way before you start operations. And also the aggregates are quite influenced by shape, grading, surface texture, which is also mostly done by geologists or like in geological labs, also in construction laboratories. Okay, just for an example, to just expand on the rocks. This is from American Highways AASHTO site. Let me just take the note here. So basically, you will have hard igneous rocks having 10% out of 100% abrasion loss, which is quite nice. These are quite good, high quality aggregates. Limestones and sandstones, they can have up to 60%, which is quite undesirable and still usable in certain circumstances, but still not a great number. And if you go into specifics, you can see like basaltic rocks or dolomitic rocks having much better resistance to abrasion. Granite is kind of midline. Limestone in general is a good material to be used. Quartzite also good, but it has chemical problems, which I will talk a little bit more. Just a side note, there are two specific types of concrete, which I'm not going into detail, which is lightweight concrete and heavyweight concrete, which has quite specific uses, such as heavyweight concrete is used in nuclear reactors as cover, as core cover, or lightweight concrete is used for marine structures that you cannot easily access to. And they use unorthodox materials such as shale or magnetite, but that's in a whole another discussion. Okay, moving on. And now that we discussed about the abrasion resistance and freeze thaw resistance, we have secondary, which we consider secondary properties, still physical properties, like water absorption. Water absorption is quite important. It really affects how a concrete is workable, or how much you need to heat the aggregate to move out the moisture. Uncompacted void contents, as you can see here, the more voids you have, the more filler you need to use, which is going to be cement, which increases the costs, increases the environmental impact, increases the waste you are having. Second one is lightweight particles. These also negatively affect any concrete. So you have to again, these all need to be identified during petrographical or mineralogical analysis, but sometimes you need to have quantified results. So you do these tests, even though if you know you have these materials. Clay content, this is quite relatively new concept. You know, the smectate, I think it's also called montmorillonite group, which is quite expensive clay. Even in small amounts, this can be really problematic in concrete. So this test is becoming a newish standard for it. So like I said, sulfate and chloride content comes back again. So we have sulfates and chlorides in soil and groundwater, and now we added to the mix the ones in aggregates, and then we will have the mixing water, then we will have the chemical additives. So we need to control the amount of total sulfates or total chlorides in a mix so that it doesn't affect the reinforcement or the concrete itself. Okay, moving on. Like I said, geology really affects what you need to do. British standards have United Kingdom specific tests that might not be used in other countries, and two of them is aggregate impact value and aggregate crushing value. These are physical tests that are done in the UK and other countries that adopt UK tests. One thing of interest is that is directly related to the geology of United Kingdom, which limestones and chalks having high amount of shell content, especially in younger, well, like I said, geologically younger deposits. So shell content, shells are obviously, they crack and disintegrate under load. So this is specific to United Kingdom. In general, other countries might not use this or might not see the need to use it. So again, geology, mineralogy, and petrography controls the production process once again. Okay, moving on. So I choose, there's multiple cases or multiple reactions, but I wanted to choose one thing that is again directly related to geology, and it can be prevented by good geological investigation, which is alkali silica reactions. And you can see they are quite damaging, and the reaction can be really fast, and you need to do really expensive repairs or maybe have to demolish the buildings. This is directly influenced by the mineralogy and weathering of the parent rock. The basic of it, you can see it, the alkalis in the cement paste, they interact with reactive silica. So quartz is not reactive in this sense. So we are talking about the polymorphs of quartz like tridymite or cristobalites, or amorphous silica such as opal. So even the smallest amount of these materials can be really reactive to the alkali in the structure. So this will cause eventually seep into the aggregate itself and start cracking. That will expand to the whole structure. And like I said, petrographic and mineral identification is quite important, which was part of my job as a quality control and quality assurance engineer in my previous jobs, to identify potential risks might be caused by mineralogy, and identifying reactive silica is quite important. In some countries, you might never have this problem. In some countries, you have to always watch out for it, but it doesn't mean that you can't use the material, but you have to progress into more detailed and more advanced tests, such as expansion test, which is done in, again, like construction laboratories. But again, geology is the first line of defense in preventing costly mistakes. So I just wanted to have this as a sample case. And moving on, another sample research about how geology is important. This comes from our wonderful people in USGS, United Geological Survey. This is quite recent, in 2020. And these notes will be distributed, and you can access to the research or any links in here. So basically what they did was in certain states, they realized some foundations deteriorated and started to crack real fast in many areas. So they made a research about it, and it came to that the pyrite, which is a sulfate mineral that is like pyrite, but the difference is pyrite is not actively interact with water, but pyrite is water soluble and reacts with water, which increases the amount of sulfates in concrete mix. Again, we are going back to the total amount of sulfates. So to identify the national sources and to prevent again making mistakes, I have to say these doesn't prevent the material to be used, but you need to know beforehand and take into consideration during your mix design. So they have this wonderful map of quarries and resources that has pyrite mineral, which can be easily used to identify, as you can see, the eastern seaboard up to Georgia, and I think this is, yes, somewhere close to New Orleans area, Louisiana, and you can see in Seattle, Washington area, or California. So if you have a construction in here, you can be a little bit in the Midwest or in these areas, you can be a little bit sure about that. It's not in the local geology to find this mineral, but if you are around these parts and if you are having problems with structures, then you can prevent this by taking necessary measures. Okay. So recycling, sustainability. Again, we like to use the word sustainability so much. Everything has to be sustainable. Everything has to be recycled or into. But is it possible? Is it possible to recycle, or is it possible to make everything 100% sustainable? Sort of, kinda. So in concrete, again, in the beginning, like I said, reliably recycling concrete and using it as fresh concrete is still developing. It's not, we are not there yet, as in the asphalt section. I will explain the differences between that. Because of the aggregates and the cement paste, they lose their properties once the reaction is over. Well, technically the reaction, the hardening reaction, is never over, but it's way past its effective time. So, but recycled concrete can be used as in road construction as sub-base material, or you can reinforce the weak soil as a replacement to using virgin aggregates. Normally, if you have a soil that is not which control weak soil or an organic soil, the standard solution is to remove the soil and use as a good quality crushed aggregate, which is quite expensive and quite energy intensive because you have to core it. But you can recycle the concrete and use that aggregate and the remaining binder as stabilizing agents in weak soils, which is quite good. The main problem is recycling concrete requires higher initial investments because you have to fish out the other parts like rebars or other elements, and crushing concrete requires quite high energy machinery. But again, it's all a balancing act. If you can compensate for the cost of using fresh aggregate, then of course it's going to be much easier. The one of the problems that is still cannot be solved is reusing the water used in concrete, because once it's in there, it's gone. But you can recycle the leftover water from concrete production in the plants, which is not too effective, but better technologies are developing in that department. And this is actually one of the most good developments in chemical admixtures that change. They almost literally tricking particles into thinking that now they are more fluid, which can reduce the amount of water to be used at 20%, which in turn reduces the amount of cement you need to use. These are quite important and quite exciting developments, and we are in the third generation, which uses this used to use naphthalene-based admixtures. Now we are using more polymer-based, more effective ones. Quite good. And we have a question. We will have the questions at the end of the session. So I'm going to move to second section. Let's see. Oh, yeah. So we will have the second one, the second manufactured item, asphalts, still quite involved in geology. Again, let's start with the basics. I hope everyone can see it. Okay, so pretty much the basics are here. When I mentioned in concrete, we have a binder, we have aggregates, we have filler materials, and we have chemical admixtures. The difference is bitumen is one of the most expensive binders in construction industry, and as you know, it's produced from crude oil, and it's the byproduct of crude oil refinement process. And sadly, there is no viable alternative to replacing bitumen. There used to be research about having artificially producing bitumen in the 40s and 50s, which didn't turn out as productive. So we are reliant on fossil fuels to production of bitumen. Hopefully, with the more shift towards rails or more sustainable transportation methods, we will see dependence getting less. But right now, we need quite a lot of bitumen. So again, the second materials are aggregates are the same. Aggregates and mineral fillers are used, but the changes, the production of asphalt requires quite intense levels of heat because you have to, the bitumen needs to be heated and made it workable. So again, we are burning a lot of fossil fuels to reach to that heat levels, which is going to change into more sustainable energy resources like wind energy, as long as electricity. But the problem is the intense heat that is required can only be reliably obtained by burning fossil fuels. That's almost another discussion. And one good thing, it's not always doom and gloom. Recycling asphalt is quite effective, and you can use recycled asphalt as new asphalt payments up to quite high percentages. And with the new development of chemical rejuvenators, you can use the bitumen over and over again, which is different from concrete. So for asphalt pavement, recycling is much reliable option. Okay, moving on. Just a recap on bitumen. It's quite flexible, easy to work, used for a long time. The byproduct cannot be used as fuel. It's quite expensive, and it's derived from crude oil. Accessibility is not directly tied to geology. You can import bitumen because it's quite easy to store it as a cold bitumen. It can be reanimated with heat without losing too much of its properties. But again, it's transporting is quite dangerous and can cause extreme disasters, which no one wants to see. Again, this is like construction industry in general is quite silent. Not many people think about how these things affect your experience, but in general, bitumen binder roads are much pleasant to drive on. If anyone has had the joy of driving in a rigid pavement, which is concrete pavement, it's quite unpleasant experience. I think they are quite common in Germany. There are some, I'm not sure about the UK, but again, if it's quite uncomfortable to drive on poorly made concrete pavements. In Germany, they perfected production of concrete pavements, which is also quite good. Again, balancing act. Asphalt is more expensive or more environmentally damaging. You can have concrete, but you will have a bad driving experience, which can lead to like crashes or just general complaint. So also, I left this one to asphalt pavements have relatively short service life, 8 to 10 years before major maintenance, because oxidation is quite rapid, and once it's hardened, once it's exposed to elements, it hardens quite fast. Okay. This is not directly related to geology, because most of the time a geologist's job is finished when they found the crude oil. I think downstream, yeah. But the bitumen composition and the volatiles versus residuals can be controlled by crude oil type. So it's not even a single homogeneous material. An oil from Azerbaijan, a bitumen produced in Azerbaijan can have different properties than a bitumen that is produced in, let's say, in Texas, but refined in somewhere else. So what you have to remember is bitumen is it's quite unique for and it varies greatly, and many refineries in nowadays they use bitumen from multiple sources, so you might not even have same material from same refinery. So that's why like bitumen standards are really strict, really controlled. So that's really affects how you design an asphalt pavement. And this brings me to the compatibility between natural aggregates. Again, we are back to geology. The physical and ionic levels of compatibility is quite important. These are quite good research topics, and there is quite advancements in this area. But the industry is can be quite slow to catch up things. But in short, aggregate mineralogy and chemistry affects how well bitumen clings to aggregate. So one of the main problems or main things we faced was the established mixed design methods are from 1920s, 1940s. So they are reliable, but they don't take a sustainable approach or longer performance into consideration. New methods are developed and used widely, especially in states in Germany. United Kingdom is also catching up, but it can be a little bit slow. Okay. Again, aggregates. Same with concrete. We need good amount of resistance and abrasion resistance, freeze-thaw resistance. Same principles, with some important differences, which is asphalt pavements require higher quality aggregates, which kind of limits where you can procure these. In general, Los Angeles abrasion value less than 20%, 25% is required, which is quite limiting, because especially quarries that are being operated for a longer time, they are now quite deep and quite in the weathered zones in general. Again, a geologist is quite important in this part, because an operation of quarry, if directed by a geologist, or if a good maybe geophysical surveys, that you can keep using same quarry for a long time, or if it's not operated good, now you have to close the quarry and move on to another one, which is getting harder and harder due to high impact of quarrying materials. So overall, asphalt just requires harder and more high quality aggregate than concrete. Okay, well, another spotlight, like in concrete, this is a concept called polished stone value, which also this affects your daily life as well, because the surface of pavements, they got smoothed and polished in time as the aggregates got exposed to tire loads, and they lose their bitumen coating. So this can cause this directly increases the braking distance, and this can cause a lot of car crashes or accidents. So this is quite important value. This can make or break a mixed design. So it's quite important about it. In general, granular minerals, that rocks that has granular minerals like granites, or rocks that break non-uniformly, like basaltic aggregates or granitic aggregates, they are more preferable, because when they crack under load, they expose fresh and more rugged surfaces, which increases the abrasion between the tires and the pavements. But limestone or sandstone tend to get smoothed and get chalky. So you will have more, like you need to have more distance as break. So this is quite important, and it uses this device that looks like a medieval torture device, which is called Hamburg wheel. This is quite important, quite expensive test that requires almost a week to complete, and it can be a determining factor between using a material or not. So you have to be sure that you have a good quality material if you want to have a high quality payment. Okay, moving on. Again, now that we have good bitumen, we have good aggregates, we have good fillers, now we have different considerations such as rutting, which I'm sure almost everyone encountered. There are like grooves in traffic lights, which caused by static loads. Rutting is controlled by multiple factors, and aggregates are again a deciding factor. Good aggregates resist rutting. And again, this is quite important in new pavement types, especially that use stone and stone contact main pavements. One thing that is similar to concrete admixtures is modifying the bitumen. This is also quite interesting, and it helps with longer performance of the payments, and also again, it changes the interactions between aggregate and the bitumen. So this is also a good research topic, which I personally quite enjoy to look into. Recycling. Again, like I said, recycling asphalt is much more effective in terms of being used as payment material. In the US, they reach around like 21% of newly built payments are built by RAP, which is recycled aggregate payments, which saves tons of raw materials and carbon emissions. It's quite easy compared to concrete recycling, but the interactions between recycled payments and new materials are still researched on. It can be much better, and hopefully this ratio will increase in time as we learn more about natural material interactions with manufactured materials. Also a great topic that I really enjoy following. So conclusion, as in general sense, we geologists, we geoscientists are shared common knowledge area. And if you remember from Sara's presentation, the concepts of the granules, the binders, and the interactions between minerals, the chemical interactions, the compositions, weathering, resistant to abrasion. These are all concepts that is inherent to us, to our knowledge, and in the industry, construction industry can benefit from hearing from us greatly, especially in prevention departments. Again, there's so much to discover, so much to work on. This is quite open to if you want to pursue a research oriented career, or if you want to pursue being someone who in charge of selection of materials. That's quite open area, and it's quite enjoyable to work in. And again, it's all about identifying risks, being preventive, being preemptive before things get damaged or things cannot be used anymore. And I believe that geoscientists can bridge the gap between construction industry, environmental concerns, costs, geology. So we can be in the forefront of these things. And almost about finish. For some further resources, I highly suggest if you are a fellow of GSL, checking Lyle collection. They have quite good amount of sustainability and materials related research. If anyone wants to pursue an advanced degree, Imperial College London has an amazing program that is tailor-made for this. It's called MSc Advanced Materials for Sustainable Infrastructure. It's under civil engineering, but I'm pretty sure as a geologist, you will feel at home with if you check the courses, you will see that most of the stuff is what you already know. For asphalt materials, you can check Payment Interactive, which is slightly harder to navigate, but it has pretty much everything you need to know about the materials that are used. For concrete, ACI publish quite good amount of standards and guidelines. For in the UK, British Aggregate Association has also quite good resources on aggregate itself, which might be more up to your street if you don't want to deal with other construction related stuff, but want to focus on aggregates. And Highways England, I think they changed names recently, maybe to Highways England, but they have quite good research partnerships and postdoc opportunities in here. If you want to do this as a academician supporting the industry, and since UK is in zero emissions goal, Highways England also trying to catch up with their research. So this might be helpful for further research. Of course, you can reach out to me from LinkedIn or through GSL. I think my email has to be on ECN webpage. And I think that's it. Yeah. Matt, thank you. I hope this wasn't too verbose. I tried my best. So I think we have a question.
Yeah, thank you very much, Sara. That was a great presentation. Like you say, we have one question. How do the physical characteristics of natural sand and gravel aggregates differ to crushed rock aggregate? And are there any different test British standards for these?
That's a really good question. Natural as is materials such as the ones you can find in old riverbeds or even dredge material from sea, which is not used as much anymore. In the 60s, in the 70s, it's turned out to be quite damaging to the environment. But there are differences between manufactured aggregates or manufactured sand or natural sand or natural aggregates. These are usually listed in their specific standards, British standards. I believe I will have to check, but I think British standards has they differentiate between natural and manufactured. So the tests are same, but the specifications can change. For example, natural materials are quite round that are not good for concrete or bitumen production, because you need that rough texture that you can only obtain through crushing them. But also you can process the natural aggregate in crushing plants as well. So but still, there to answer your question, yes, there are differences. Yes, British standards or American standards, ASTM, acknowledge this. And but in general, they use the same tests, but they are evaluated on their own, if that answers your question. But I would be more than happy to provide some examples through email if you leave your email here.
Great, thank you. I think it's fascinating to hear you talk with such passion about a subject, same as Sara, which perhaps a number of geoscientists never really considered part of the geosciences. Perhaps it'd be good to give a little bit of a background on what you did as a student, and if you had any advice for perhaps current students, similar to what the question for Sara, or early career people who may be thinking this is an option for them, and how they could look to join the industry.
Absolutely. Well, like I said in the beginning, I started as in a geochemistry and petrology lab, which I liked for personal reasons. I like laboratories. The thing is, these jobs might not be easier to find unless you are looking for. So these, especially in industry, these are most of the time they listed as QC engineer or QC or QA/QC. So you might never come across something like materials engineer. Sometimes you do. I see. Sometimes I come across listings like that. How I started, like I said, I was working in a geochemistry lab, and my professor back then, he recommended to me to a construction company that needed a laboratory manager. someone to run the laboratory in Northern Africa. So so I just accepted the job, and then eventually, gradually, you get exposed to the other aspects of, because in the beginning I thought I was just going to do soil testing, or like some geotechnical. Then I realized that it's going to be much bigger than that. I mean, it wasn't like I didn't aim to do this, but in time I realized how much we have in common. So I strongly suggest checking with like construction companies, because they are quite open to having someone with geological background and knowledge of aggregates and rocks, because that's not in generally within the civil engineering curriculum. So we have that knowledge. We can identify the problems that other disciplines can look over. So that's the thing. Like this is starting from reaching out and like applying to jobs that are more focused on quality. The keyword is like quality control, quality assurance, and read between the lines if they mention any kind of like aggregate testing, or like concrete testing, or asphalt testing. So that should be what they should be aiming for if they are looking for a job. As an academic career, like I mentioned, as far as I know, I'm sure like there are other. Imperial College London has a good, really good master's program for this, and they can reach out to professors in there, and or they can reach out to Highways England or National Rail, because National Rail also they use quite a lot of aggregates in railways and their structures. So yeah, pretty much that's how I can just think of like how can you start with this.
Lovely, thank you very much. So that brings us to 7:30.
Mm-hmm.
I think we'll wrap up there.
Yeah.
So just offer a huge thank you to both Sara and Serdar. I think they were both fantastic presentations, and the ECN really does appreciate you offering your time and your experience for us and our members. Also, thank you to everybody who attended. I hope you found it enjoyable. As we say, this is a launch of the lecture series, so please join us next month. Next one's titled Unconventional Career Pathways, Where Can Geology Take You? Every month is going to be run by a different committee member, so if you do join us, you'll get to meet the committee throughout the series. Do follow us on social media. We're active on Facebook, LinkedIn, Twitter, all under the same handle. It's where we post all of our events, and do get in contact if you have any thoughts or topics you'd like to discuss during the lecture series. We run all our events for our members, and we're all volunteers, so we are here to help you. So please do reach out to us. Also, we're launching our webpage again, so do keep a lookout for that on the GeolSoc webpage. It's getting completely revamped in the next week or two. That'll be going live, so do check it out. So thank you very much, and we'll see you next month.
Yeah, thank you.